So one thing about coordination complexes is they have very defined geometries. We'll talk more about, I guess, what determines the geometry and the number of ligands a metal can bind. But for now, we'll just talk about really common ones. So one of the most common ones is when you bind 6 ligands on a metal, so Ml6, so 6 ligands. So this is typically octahedral. So we have a very defined octahedral geometry. Okay, octahedral 90 degrees, all around, symmetric. Other common coordination numbers would be 4 ligands. So when we have 4 ligands, we have two major possible geometries and kind of the continuum in between. So we could have something that's totally square planar. Square planar. Or we could have something perfectly tetrahedral, right, with 90 degrees versus that 109.5 degrees. So voila, we could have 5 coordinate, and then so this could be trigonal bipyramidal. Or we could have square pyramidal. Right, so square, pyramidal, trigonal, bipyramidal. So as a result of these very defined geometries, we can end up with isomers. So just like in organic chemistry, you can have different ways of putting things around that central atom. Only now we have a lot more options because we have many more geometries that are defined. So I'll give one example that we've already seen before, which is suppose that we have a complex. So I'll kind of denote it like this. If we have a complex with 2 types of ligands, and then one of them we have 4 of, and one of them we have 2 of. So ligand A and ligand B, so we have 4 and 2. So 2 possibilities that we could have. I guess I'll do one specific example, is that the Werner type complex we've been talking about. So cobalt with 2 chlorides and 4 ammonias, and then I guess that'll be cationic. We could have something like, oops, NH3, NH3, and I'll put a cationic. Okay, so this, we could have the chlorides 180 degrees from each other, or we could have the chlorides 90 degrees from each other. 3. Those are ammonias, by the way. NH3, NH3, NH3. And then so this would give us, this would be called cis, and this would be called trans. So trans, they're across from each other, and cis are next to each other. So this is determined by the chloride ligands because the ammonia ligands are kind of just wherever the chlorides aren't in the octahedral geometry. This could also happen if you have a square planar 4 coordinate thing. So as an example, if we have platinum with 2 chlorides and 2 ammonias, we could, again, have them 90 degrees to each other. Or we could have them 180 degrees from each other. Excuse me, the dust. So again, this will be cis, and then this will be trans. I do want to point out this is a molecule that's important for cancer drugs. So cisplatin is the active one, and then transplatin is not. So again, which isomer you have is really important. OK, so these are kind of geometric isomers. Oh, another example would be, hope I have enough room, if we have some situation where we have 3 of each ligand, Ma3B3, then we could have 2 situations again. So we could have, OK, I'll just do another cobalt example. Let me erase so I have room, just so I'm not so cramped. OK, hopefully everyone has written all this down. So if for our Ma3B3, we could have, let's say, our cobalt with 3 chlorides. We could have the chlorides all 90 degrees from each other. And then that means we have our ammonias over here. And then we could also have our cobalts, or the chlorides, maybe 2 of them are 180, and then 1 of them would be 90. So then the rest of ammonias would be here. Keep in mind that I could also use the ammonia ligands positions as kind of direction because they are the same as what the cobalt or as what the chlorides are. So here the ammonias are also 180 from each other with the 90 in the middle. So these are the 2 different possible isomers of it. You can see if I rearrange ligand positions, they'll be the same. So be able to do that. And then so this is called FAC for facial. And then this is called MER for meridional. So this is meridional because you can see it's kind of going around the belt. It's this way. There's 2 across. This is facial because if we were to draw it as sort of an octahedron, so let me see if I can draw an octahedron. Here's my central square. Here are my axial ligands. So by taking these 3 over here, what we've done is, so let's say these chloride atoms, we've described a face through those 3 atoms. So that's facial versus meridional. So those are another type of geometric isomer that we have when we have due to our geometries. OK, so in addition to these geometric isomers, let me quickly erase, we can also have, just like in organic chemistry, we can have stereoisomers. And then so that means that we could have optically active compounds. So coordination compounds can be chiral. I guess in some ways those isomers can be considered stereoisomers. These can be stereoisomers too. But let's talk about chiral coordination complexes. So you could make a chiral coordination complex a tetrahedral one, just like we could for in organic chemistry. So the main goal, of course, is to not have a mirror plane, so you don't have superimposable mirror images. So I won't write that all down because everyone's taking organic chemistry, so you should know what chiral means. So a tetrahedral complex would be easy. If we have 4 different ligands on it, it's got to be chiral. So, but for an octahedral complex, so let's say chiral optically active. OK, so for an octahedral complex, here's my kind of octahedron. I won't draw the metal in the middle, like so. So if I have this all the same ligand, it's really easy to have a mirror plane in an octahedral geometry because you have such high symmetry. So for octahedral complexes, helium ligands are a really useful way to introduce optical activity. OK, but of course, it depends on where you put your helium ligands. So for example, suppose I have my metal here. And suppose I have 2 chlorides here, but then I have 2 chelating nitrogen-based ligands. This could be ethylene diamine, it could be BIP. So this one, of course, has a mirror plane. So this is not chiral. Right? We could draw a mirror plane right down this middle axis and have these 2 ligands kind of mirror onto each other. So this is not chiral. But on the other hand, if I rearrange these same ligands on this complex, so again, I have my octahedral framework. So if I move the chlorides to now be cis to each other, and then we have our ethylene diamines or chelating ligands this way, what you'll see is that there is no way to do the mirror plane So if we, let's say, do the mirror plane in the plane of the board, so that way the chlorides don't mirror on each other, or they mirror onto themselves, what we'll see is that this nitrogen will mirror onto this one, but this nitrogen will stay on itself. So what ends up happening is that we end up with a different isomer. So let me kind of illustrate that because I guess that was confusing. So here's my mirror plane. We do mirror plane this way. And let me redraw what's happening. So, okay, I've mirrored. And now let's draw where our atoms are. Here's our chlorides. And let's see, so nitrogen's over here, nitrogen's over here, nitrogen's over here, nitrogen's over here. So these should be non-superimposable. So if I kind of, no matter how I rotate these, so if I move the chlorides this way, if I kind of turn this around, we no longer, this will not be, these ligands will not be in the same position. So it's kind of, that's why this is chiral. These are two enantiomers of each other. And that's because if we had, because of this kind of backbone linkage of the chelating ligand, if we removed it and then we had 4 ammonias, of course it would not be chiral because we would be easily able to mirror itself. Yeah, another common example is, let's say if we have 3 chelating ligands, so if we have, let's see, ru-bipi, so ruthenium with 3 bipi ligands on it, which again I'll abbreviate as those nitrogen donors. So here, oops, excuse me. Let's say this one, and this one, and this is overall 3 plus. What you'll see is that this actually has kind of like a propeller shape. So you could rotate it on with like some sort of a C3. But if we do the mirror plane, this will be going this way. Nitrogen, nitrogen. Now we've actually changed the direction in which the propeller goes. So this is also chiral. And then, so basically, you can kind of just like practice drawing it. We'll do some practice examples in class and kind of get a feel for these optically active isomers of coordination complexes.